Hi everyone, can you hear me? Okay, so yeah, I'm Myoungwon Jeon. I'm a postdoc at the Arizona. So first of all, I want to thank the organizers for inviting me. So today I'm going to talk about formation of the first galaxies and their connections with the local dwarfs. But I'm going to mostly focus on the first part, formation of the first galaxies. And at the end of the talk, I'm going to talk about their connection with the local dwarfs. So let me start with the cosmic history of the universe. So that figure, okay, it start working. Okay, so this figure is just showing the cosmic history of the universe from the Big Bang to the present day universe. Right after the Big Bang, the universe was very quiet and dark. It seems like nothing is going on. However, like underlying structure is still growing, and then at some point, like the first generation of the stars were formed in the mini halos. And when the first stars were formed, like the universe has been changed dramatically from the very simple universe to a very complex one. And those first galaxies were formed in a mini halos, and then they got evolved into larger systems, and eventually at reddish to tannish, like a first generation of galaxies were formed. So even though like that whole period is just 7% of the total cosmic age, but like a dramatic change happened at the time. So like when it comes to like open questions in the early universe, like especially for the reionization, the most important questions will be when and how did the reionization occurs, and also what kind of sources really caused reionization. So to answer these questions, we have to know the source for the reionization. So it is believed that like the first generation of galaxies kind of initiated the onset of the reionization. So we have to know the first star properties to answer to those questions. And also to know the characteristics of the first galaxies, we have to know the first stars. Because the first galaxies actually were formed in initial conditions that were shaped by the first stars. Especially we have to understand these questions, like how do stellar feedback from the first stars influence the first galaxies. So in here, like these all questions in the early universe are all connected. So we have to know each other, like first galaxies and first stars, to understand the reionization. So there have been enormous effort, like a theoretical effort to understand the first stars and first galaxies. We always start from the very simple one and the little bit complex one. And at the same time, like observations have been pushing the redshift frontier by discovering most distant galaxies. And this discovery will continue to accelerate due to like James Webb Space Telescopes or other like large ground 30-meter telescopes. So we're gonna have like a full picture of the cosmic history in the early universe. So the most distant galaxies discovered so far is around redshift 11, like we call it GN Z11. So this one is a quite massive galaxies with a stellar mass of 10 to the 9 solar mass. And in addition to that, we have like 14 additional galaxies with spectroscopic redshift conformations larger than redshift 6.9. So we know that we're gonna observe, we already have like a small sample of the high Z galaxies, and then we're gonna observe more first galaxies from GMT and other telescopes. But what about first stars? Can we really detect first stars from like JWST? The short answer will be probably not, because like they are so faint to be detected even with the JWST. However, like there will be another possibility to like find first stars. They will be like when through their death, like if they died as a very powerful supernova, like a pair instability supernova or gamma ray burst, maybe we can find some kind of evidence of the first stars. And also the other possibility of the evidence of the first stars will be like by looking at the local universe. Maybe local ultra-faint dwarf galaxies might have some kind of a hint of a first generation of stars. I'm going to talk about this one later at the end of the talk. So even though we are not going to detect the first stars, but it is very important to know their properties, because first galaxies were formed from the first stars. So then the question is, what is the first galaxy? So can we define first galaxies? How can we define first galaxies? From theoretical point of view, that could be a little bit different from the observational point of view. We define first galaxies as galaxies hosted by atomically cooling halos. So unlike the mini halos that can be easily disrupted by the stellar feedback from population 3 stars, atomic cooling halos were massive enough to overcome stellar feedback, and eventually they was able to sustain continuous star formation. Then how can we make first the galaxies from the simulations? So we always start from the simple one, like from single sample. Like in here, I'm showing the small box simulations with the zoom-in simulations. So to do that, we can have a really high resolution, like 30 solar mass for dark matter and 5 solar mass for baryons. So that means we can resolve individual population 3 stars from these kind of simulations. So that allowed us to detail the structure and also star formation, but it only provided only one single galaxy. So people needed more samples, so we went to a little bit larger scales, like a mini box scale. But like the call middle is because like compared to reionization simulations that usually performed on a like a 50, 100 megaparsec scale, that is still like a small box. With that, we will have like 100 to 1,000 galaxies. However, because we increased the box scale, so we have to sacrifice resolutions. The achieved resolution will be like 3 orders of magnitude smaller than the like small box simulation. But instead, we can do some kind of a statistical study, like constructing luminosity function or getting some kind of relationship between stellar and halo mass. And also, like recently, as a compromise approach, people started having like a multiple zoom-in simulations with a kind of a intermediate resolution. So those are the way of forming like a first galaxies from the simulation. Then let me show you one of the movie, like that is for one single first galaxies from top left, like dark matter and gas density, temperature, and metallicities. And the central white dot is the feeder radius of the central galaxy. It will gonna grow over time. So at first, you can see some kind of feedback from the individual population 3 stars from neighboring halos. And up to register 13, there was no metals inside of the galaxies, and there is a metal from another like neighboring halos. And at around register 13, like the very first supernova like going off, like enriching the medium. And you can see like a very powerful star formation followed by supernova feedback. So I run the simulations up to register 10. And then you can see like a highly evacuated gas from the stellar feedback from population 3 stars. So I'm going to explain like about this galaxy in more detail. So you can see like while forming one single galaxies, there are so many things is going on. Like that is due to the feedback from the population 3 stars, like thermal feedback such as photoionization heating, supernova feedback, black hole feedback, and also we have to follow the chemical abundances as well, like ejected from the supernova feedback. So before explain the individual star feedback, we have to know what the first star was. So when the first stars were formed, the universe was very different from the present-day universe because there was no metals at the time. So meaning that we naturally produced very massive stars, like order of 100 solar mass. This is because there was no like metals, and then meaning that the gas was not able to fragment into smaller scales. So the gas was formed out of very massive gas cloud, like creating all the material, forming very massive stars. So this one is the kind of characteristics of the first stars. Like they formed around register 30 to 20 in a mini halo with a mass of 10 to the 5 to 6 solar mass. And then their main coolant was molecular hydrogen. There were no metals. And then one of the characteristics we really want to know is their mass. So how massive they were. So when the community, like first star community started, we believed that they is very massive, like above 100 solar mass. But that has been a little bit changed to a little bit lower region because we started putting radiative feedback from a protostars that really like terminate gas accretion into the protostars, limiting to like a 10 to 60 solar mass. But recently, like some study suggested, like based on like 1,000 individual population 3 stars, they provided the range between 10 to 1,000 solar mass. So we still don't know like what the population 3 stars mass was, but like one thing clear is that they were massive compared to the present-day universe stars. And then why do you care about their mass? This is because depending on their initial mass, their fate will be different. For instance, if their masses was between 10 to 40 solar mass, they died as a quark collapse supernova, like a conventional quark collapse supernova. And also, if their masses was between a very particular mass regime, like 140 solar mass to 260 solar mass, then they died as a pair instability supernova, like a very energetic supernova. And also in a other range, they just directly collapsed, forming a black hole. And also, depending on how they dies, accompanying feedback will be also different. So when the stars were formed, like H region was generated surrounding a star, and then depending on like their remnants, like black hole or supernova feedback, X-ray can be emitted or like metals can be ejected from the supernova. And also, if they were formed in a binary systems, then if one star is accreting the material, the black hole is accreting from another stars, then X-ray will be emitted. So sometimes we call it high mass X-ray binaries. So all these different feedback actually shaped the initial conditions for the formation of the first galaxies. So this one is showing one of the supernova explosion with a progenitor mass of about 40 solar mass. So initially, H2 region was generated. So that is actually penetrating along this direction that is kind of perpendicular to the density filament structure. So at the end of its lifetime, it exploded as a supernova. You can see like a metal in the last panel. There will be. Yes, there will be like metals will be ejected from the supernova, and then like gas will be like disrupted tremendously. So one thing I really want to understand is like how destructive a single supernova can be. So you can calculate that some kind of like a delay time between the end of the first stars to the next generation of star formation. So for instance, like in here, it basically says that like it would take a couple of tens of a million years for the one single quark collapse supernova, but that will be a little bit shorter compared to the delay time by a single pair instability supernova that can be like more than 200 mega year, like comparable to the Hubble time. So that means depending on the mass of the population 3 stars, the transition from population 3 to the second generation of stars, so-called the population 2 star, can be order of 10 million years, or it could be like longer than the Hubble time. And also another interesting feedback we have to understand is the X-ray feedback. So if there is a possibility that first stars can be a black hole, so this one is showing the black hole growth from the population 3 stars over time. I'm comparing two simulations. One is the with X-ray, and the other one is without X-rays. So that is the black hole mass starting from the 100 solar mass. With X-ray, there is no growth at all. But without X-ray, you can see like it can grow up to 10 to the 4 solar mass by radius to 12. Actually, that like a strong impact on the accretion on the growth of the black hole can give us very interesting implications. One of the open questions in the early universe is how supermassive black holes was able to be formed within a very short amount of time, like less than billion years. So there have been some suggestions. One of them is that maybe they might start from the population 3 star black hole with the 100 solar mass, and then they grow over time with the Eddington limits. But as I showed in the previous slide, like X-ray feedback was so efficient, like preventing the black hole growth. So this scenario could be unlikely. So another like alternative way of forming supermassive black hole will be direct collapse of primordial gas in a atomic cooling halos. So nowadays, people are more focusing on the direct collapse scenarios rather than the seed black hole scenario. So X-ray can do further than that, actually, because X-ray can penetrate into the IgM and heating the gas in the IgM. So you can see like a difference between left panel and the right panel. Right one is showing the filamentary structures with X-ray feedback. So you can see like very smoothed out with the X-ray feedback. This smoothing can be quantified by computing some kind of a clumping factor. Clumping factor means just how clumpy the IgM was at the time. So with X-ray feedbacks, the clumping factor can be reduced by a factor of 2. The reason we care about the clumping factor is because when it comes to reionizations, we always trying to compute the ionizing photons, the total ionizing photons to reionize the universe. But that number can be changed depending on the clumping factor. If the IgM was clumpy, then we needed more ionizing photons to reionize the universe. So this kind of X-ray heating from population Dwarf stars can be tested with upcoming radio telescopes, using 21 centimeter. Okay, so X-ray feedback and supernova feedback, we can include all of them, and then we can form first galaxies. So this one is actually the same simulations I showed before, but for the little bit larger scale. So you can see individual population stars are forming in everywhere. And at the end of the simulations, I found around 183 population Dwarf stars. And then you can further classify into individual remnants. I had two parent-stability supernova. And so I marked different remnants at a different color in here. So at the end of the simulations, I got this snapshot. So that galaxy's property is like this. Their mass was 10 to the 8 solar mass, and then their stellar mass is about 10 to the 4 solar mass. This is very small galaxies. This is similar to the local ultra-faint dwarf galaxies like Segway 1. And the one thing I want to point out is that in a metallistic plot, there is no primordial gas anymore. So first galaxies were already metal-enriched systems rather than primordial systems. And the next question we have to ask is can we really detect these systems? So we can compute the flux, and then that turns out to be 10 to the minus 2 nanojansky. That is 2 orders of magnitude smaller than the JWST detection limit. So unfortunately, this galaxy will be too faint to be detected even with the JWST. But however, if we have more samples, so in the introduction, I mentioned this middle box simulations, that is especially Renaissance simulations, and then they simulated 3 different regions, and then they combined all the galaxies having 1,000 galaxies. In here, stellar mass as a function of a halo mass. I marked my simulations in here 10 to the 4 stellar mass. So I want to point out how stellar mass can change at a given halo mass. Even though halo mass can be fixed at 10 to the 8, but you can have 1,000 stars or 10 to the 7 solar mass. So that means stellar mass can change by 3 or 4 orders of magnitude. Actually, that is due to the stellar feedback I showed you before, in the movie. Those small galaxies were very vulnerable to stellar feedback, so that resulting stellar mass can change a lot. So for the JWST detection, we needed to have at least 10 to the 6 solar mass stars, and then those galaxies will be only detectable by the JWST. And that corresponds to UV magnitude of minus 16. So this one is the synthetic spectrum of the one single galaxies with a stellar mass of 10 to the 7 solar mass, which is a very massive galaxy. That basically says that compared with the JWST detection limit, we will be able to find this galaxy either by UV continuum or a nebula emission. And the next question will be, then, how many galaxies actually the JWST is going to detect in one field of view? with a deep exposure. So Andreas Pauli actually computed this number, a total number of galaxies in one single field of view. And then like it is kind of like a busy plot, but basically says that like it can change from 100 to 1 million galaxies. But when he computed this one, like he assumed different like stellar populations. One of them was that the stellar populations can be primordial, totally primordial. But in the movie, I showed that like the first galaxies were already matter-enriched systems rather than like a primordial one. So that assumption for the primordial stellar populations will be unrealistic. So we have to rule out that like big numbers. So the most reasonable number will be less than 100. So we're gonna have less than 100 galaxies in a one field of view of JWST with a deep exposure like a 1 million second, 10 million seconds. So, but the number can be changed depending on where we are looking at, actually. So in here, I'm showing 3 different regions, like a very clustered region at very high redshift, and then normal region at 12, and in like a little bit lower redshift at void. So in here, like yellow one is showing the galaxies that is detectable with the JWST ultra deep field, and then magenta means like lens the JWST detection with a magnification over 10. So it says like about 10-ish galaxies will be detectable in the clustered region, but even in a very high redshift, like a redshift 15. But that number can be changed to like just a single galaxies, a redshift 12 in a normal region. And in the, even in the like a lower redshift, a redshift 8, in a void, we're gonna have 10-ish galaxies because the structure was already evolved, so that gives us a lot of bright galaxies in low redshift. So another quantitative way of studying the number of galaxies will be luminosity function. So luminosity function just say like the number of galaxies at a given volume as a function of magnitude. So that is the JWST detection limit, that only those galaxies will be detectable. So high redshift people always talk about like Fein and slopes. That here is meaning that like they always wanted to know like how many Fein galaxies there were. So observations, that is the Schechter field in here as a dashed line, white dashed line. So that predicts some kind of steep slopes, meaning that there were a lot of Fein galaxies. But theories, like simulations, those are simulations, are predicting some kind of like a flattening or even turnover, meaning that lower Fein galaxies existed compared to the observations, like inferred from observations. So if that is true, then what causes that kind of turnover? Why there were fewer galaxies than we expected? So that can be explained by like inefficient star formation in a small galaxy, or like a star formation in those small galaxies were easily quenched, or like quenched by either by stellar feedback or reionization, or by both. And also, people really want to know the mass scale for that turnover. So sometimes people suggest 2 times 10 to the 8 solar mass at high redshift to like 10-ish. So, and also like this kind of tension between observation and simulations can produce a problem when we are trying to understand reionization, because this lower number of small galaxies will produce underproduction of ionizing photons relative to what is needed to reionize the universe. However, that tension can be mitigated by taking into account escape fraction. Even though the absolute number of Fein galaxies could be smaller than what we expected, but they could be very active ionizers. Maybe ionizing photons were more easily escaped from the small galaxies. So that shows the escape fraction as a function of a halo mass. For small galaxies, like less than 10 to the 8 solar mass, all of the ionizing photons were escaped from the halo. So we need to know like many quantities, like stellar populations, whether there is primordial or like matter enriched, then how much matter enriched, and also how many galaxies there were at the time, and what is the escape fraction of the individual galaxy, and then what was the condition of the IgM. So we need all this information, and then theory actually can provide those quantities. So even in lower redshift, like redshift 6, we still observations and theories haven't reached like agreement. Like this one is showing faint slope of the luminosity function. You can see sometimes observations are predicting like steep slope and then a little bit shallow. So still we needed to we need more observations and theoretical work to reach like agreement between these two. But in a JWST era, we're gonna have a lot of observations, high Z galaxies, and at the same time, we have to theories to provide more robust predictions for the physical quantities of those small galaxies based on more sophisticated modeling. And at the same time, not only just one single galaxy, we have to provide multiple samples to provide some kind of statistically meaningful quantities. Okay, let me switch gear a little bit to the local universe. As I showed in the during the talk, I explained that the small galaxies were very vulnerable to stellar feedback. So star formation can be easily quenched. So what if reionization really quenched all the star formation in such small galaxies? Then, especially the second generation of stars that were formed out of gas that was just shaped by the population 3 stars, especially out of the contaminated by the population 3 supernova. Then maybe we're gonna have some kind of hint of a first generation of stars in the local fossil galaxies, especially ultra-faint dwarf galaxies. So actually this kind of scenario seems to be working because observations are showing that is the color magnitude diagram of the ultra-faint dwarf galaxies in the local universe. That basically saying they are very old, their stellar population seems to be very old. And if you look at the metallicity, and they seems to be extremely metal poor. So stars are very metal poor and old, meaning that they formed very early time. So we can test this kind of scenario, we can take local dwarf galaxies around the Milky Way size host halos, and then we just rerun the simulation from the beginning by putting population 3 and population 2 star formation. So this one is kind of the movie, but I didn't stop it at redshift 10 or 7, but I continuously run the simulation down to redshift 0. At redshift around 7, you're going to see the impact of reionization. So there are star formation from each mini halos, and at redshift 7-ish, reionization happened, and then everything was heated up to 10 to the 4 Kelvin, and then very all the star formation is kind of quenched by reionization. And then I ran this kind of simulations for 6 different halos. And then this one is just showing the star formation rate as a function of time. So you can see that star formation is quenched by reionization. There is no star formation at later epochs. But for the little bit massive systems, there will be some kind of residual star formation even at redshift 0. So the kind of the mass scale that determine whether the star formation can be quenched or not will be around 10 to the 9 solar mass. So, and then that is also in a very, that is fitting well with just the relationship between halo mass and stellar mass relationship, and also agree with the other work. So then how can we really say that stars actually if affected by the population 3 stars? So we can look at the chemical abundances. In here, I'm showing the carbon abundances as a function of their metallicity. The gray colors are showing simulations. So one thing people always wondered is the existence of carbon-enhanced metal-poor stars. So we observed carbon-enhanced metal-poor stars in the local ultra-faint dwarf galaxies, but we don't know what that is. And then we speculated that might be from the population 3 stars. So population 3 supernova produced a lot of carbon, and then the second generation of stars were formed out of that gas that containing a lot of carbons. So actually, our simulations was able to produce like a carbon enhanced metapore stars. That is one of the like signatures of a population 3 stars. And by comparing with the observations, like the colored circles are showing the observations from ultra-faint dwarf galaxies. It is pretty good match. And also for alpha elements, we also found like enhanced alpha elements that is predicted from observations for stellar populations in the ultra-faint dwarf galaxies. So abundance seems to be right and shows very good agreement with the observations. And also, like we can further distinguish between like if that stars can be affected by population 3 or population 2, like by analyzing, like by comparing different metal species, like carbon to iron value comparing with alpha to iron value. And that shows very different trends, like a kind of opposite trend depending on population 3 and population 2 metal yield. So we will be able to distinguish these kind of population 3 signatures based on this distinctive trend. So another way of studying like first stars in the local universe or a little bit high redshift is like through diameter Lyman alpha systems. Recently, Ryan Cook reported like they found a neutral gas with extremely metapore metallicity, like iron to hydrogen value is like -3 and redshift 3. And then they don't know what that is, like how like those metapore gas cloud can be formed. They speculated that there could be some kind of a signature of population 3 stars. And also we can test this kind of things, like we also produce metapore high density gas from the simulation, so we can get some kind of a synthetic spectrum, and then we can compare with the observations. So this kind of approach to study first to stars from the local universe or like a kind of a DLA is kind of promising, because like we're gonna have a lot of data, like especially chemical abundances of metapore stars and gas by kind of like a big telescope GMT with improved spectroscopic sensitivities. Okay, so here's the perspectives. So we are entering an interesting era, like where we can feel the final gap at redshift to around 10-ish, and then we're gonna have like a full picture of the early universe, and also full picture of the cosmic history. And then there will be a lot of observations, the high Z galaxies, they were going to provide observational constraints on the first stars and first galaxies. And at the same time, theory should provide more samples and also more robust predictions for those observations. And also, like another way of studying first to stars will be like by finding the faster galaxies in the local universe. Thanks.
Good talk, Jay. I have a question. So you talk about how the smaller galaxies in the early universe can leak a lot of ionizing photons. Almost all of their ionizing photons actually escape. But then you also say that the reionization of the universe quenches that star formation. Are those processes not contradictory? They're the things ionizing it. Are they then being impacted by themselves before the rest of the universe?
Yes, we have to. So that is one of the key things we have to figure out. Okay, here. So yes, theories are predicting very kind of turnover. But even though that, so we also worry about caring about what the mass scale of the turnover will be. But as I said, even though the absolute number of small galaxies could be lower, however, so based on the calculations, if escape fraction of those small galaxies was really high, more than 30%. Then we can we were gonna have enough ionizing photons to reionize the universe. So these kind of two quantities will be constrained, will be determined by like upcoming observations, and then that is the most important quantities we have to constrain.
Following up that comment, we do large volume reionization simulations now, which don't have the internal substructure resolution of these zooming calculations per galaxy, but involve volumes of order 100 megaparsecs with fully coupled radiation hydro. And they do show the feedback on those low mass galaxies shuts them down. What they show is that when reionization has not yet reached the patch of dwarf galaxies, it is able to form stars. It responds to reionization by shutting off subsequently. But those galaxies in these simulations that are below 10 to the 9 solar masses are not dominating the total number of ionizing photons. It's above 10 to the 9 that seems to really dominate reionization.
So when you simulate the black hole accretion and high redshift, what's the typical Eddington ratio?
Okay, Eddington ratios I have plotted here. So I didn't explain the top panel, but that is the accretion rate, and then that is the Eddington limit. So like with the X-ray feedback, it is like much lower than the Eddington limit.
This seems to be quite low canyon growth with such a very high massive black hole.
Yes, but like I'm tracking just up to reddish to 10. Okay, so like, but you have to go all the way to reddish to 6. So and still, like if that's the absolute like accretion rate is low, but like it is like like strong enough to suppress black hole growth at 100 solar mass. Like if the black hole mass was larger, then like we need more like a larger value for accretion rate. Yeah.
So some of the work you showed about printing low mass galaxies focus on long-range dwarfs in Milky Way-like halo. So, and there are other processes that can happen around a halo than just reionization and quench star formation. You've got lots of environmental processing, which is evident in the morphology density relation of these low mass galaxies. So we're starting to find more of these galaxies in that very low mass range, but they're out in the field and they've not been quenched.
Mm-hmm.
And we're still in the sort of small number statistics, but they're hard to find, very small degree range. But we are starting to find more of them. So I'm curious how that fits into this picture. And in particular, I wonder if you have, you showed that one plot that all of the galaxies were pretty much quenched. I wonder if there is some percentage, if you do enough runs, that don't get quenched. I wonder if you could just comment on that.
Okay, so for that one, like yes, we have dwarf galaxies out there in the field that is not quenched, but that mass scale will be larger than that, the simulated galaxies. So these simulated galaxies are like 10 to the 9-ish halo mass, but for that, dwarf galaxies will be the order of magnitude larger than the simulated galaxy. And yeah.
So some of the ones in the field we're actually finding are as best you can estimate a halo mass below that threshold.
Yes, we can estimate. But one thing I didn't consider in here is that so I simulated the field of the galaxies, meaning that I didn't take into account the environmental effect like RAM pressure stripping inside of the Milky Way. So that is only effect of the reionization. So like if we simulate the dwarf galaxies within a Milky Way, like taking the RAM pressure stripping, then there will be more suppressed star formation. Yeah, that is kind of like upper limit value.
So do you simulate the reionization or you put it?
Yes. Yeah, that is not the coupled with ready to transfer. Like that is just the flashlight one. Like I just use the table like ionizing photon heating rates and then just to put the number. Like it is not realistic like a Bohr is doing, like realistic, like ready to transfer for reionization.
Yeah, would you want to reiterate the physical mechanism that provides X-ray feedback that prevents the wrong particle growth?
Yeah.
Any last questions?
I'm kind of puzzled. What do you think X-ray feedback is important? But the quasars are most luminous in the UV. UV is dominating the energy budget. So, so why do you think X-ray is more important than UV?
So, no, X-ray. In this simulation, I also accounted the UV from the star itself, but I cannot say if UV is more important because I put the UV in two simulations but I just comparing two simulations with the X-ray and without. So but I put it the UV at the same time, so I cannot say to that. But for this kind of simulations is from the just a single mini halos. But for a quasar, we believe that they formed from the very high density peaks rather than very small density peaks like this scenario. So at that cases, we will be able to have supermassive black holes starting from the very massive seed. So rather than 100 solar mass seed black hole.
All right, I think that's a good place to stop. Let's thank Myoungwon again.